It's what?
The hood is fine.
Yeah.
It's working.
Oh my God, lies. Thanks, Sid.
Alright,
Okay.
So, yeah, basically after you can localize and you have a map, you can create a set of waypoints in the map and you can use peer pursuit to track those waypoints. So the lesson plan today is we're gonna kind of switch the context into talking about how a normal or a usual autonomous vehicle planning stack look like. And then we're going to talk about the peer pursuit tracking algorithm. And by the end of this lecture, you should be able to do something like this. So on the left is in the simulator, and the purple line is basically a list of waypoints that you want to track around the track. You can control, I think it's better if I just don't use this. And you can control the vehicle steering basically to follow those waypoints clearly. As you can see, it's following the waypoint really nicely here. I think this is an older version of the simulator. We've added some steering delay in there, so you should be able to get as close to the real car as possible now. And on the right is basically one of Matt's entry to one of the races that we held in Montreal. This is running peer pursuit around the track. So there is a tech report. As you can see, this thing is from 1992. It's not anything new, but it's very effective. That's why people are still using it these days. But this is the tech report that detailed all the math. It's very simple math, but it's where the original one's from. All right, so let's start from talking about how autonomous vehicles usually have their planning and control stack set up. Usually, in a very general case, you'll see something like this, where the whole software stack is basically split into 3 different components. So on the left, you have the sensors and perception component. Basically, this is where all the camera sensing, all of the LiDAR sensing happen. So it could be very low level, like what we have, you're basically just receiving an array of laser scans. Or it could be higher level where you're receiving, like, say, bounding boxes from your detection algorithm, or like optical flow from whatever algorithm you choose to use. And that information from the sensing is then passed to basically a planner that deals with this information and comes up with a plan. So we usually put the planner on different levels. So in this case, we have 3, basically that work on different levels of the planning task. And then lastly, you have the car itself, or what we call a control component, where you receive a task or like a trajectory from the planning stack, and you actually actuate the car to follow those trajectories. All right, as I said before, the sensing module, basically you can have a bunch of different sensing algorithms running, right? This is, for example, a simulation in GTA 5. So you can have like your RGB image, your depth cloud, optical flow. I think that's detection on pedestrians, the bounding boxes. And you also have something like segmentation. Those are all the information that's possible from that you can provide from the sensing module to the planning stack. For the a simplest division between like a hierarchical planner, we usually have a mission planner on top. Basically, this planner tells the vehicle what's the overall goal. So for example, if you're a delivery robot, your overall goal is just to pick up stuff from the grocery store, from your warehouse, and then deliver it to someone at their apartment, at their house. Or if you're an autonomous car on the street, you usually have a start point and then a destination that you want to go to. And that's what the mission planner is for. One level down, you have the behavioral planner. Basically, this planner will dictate or create the rules for the vehicle in different scenarios. For example, if your autonomous vehicle sees a pedestrian in front, you should always give way. So that's one of the rules. Or if you're at a left turn, if you're at a left turn without a left turn light, you always wait for the oncoming traffic to clear and then you do the left turn. So that's what the behavioral plan is for. It usually controls these set of rules which you have to follow. And then one level lower, there's going to be a local planner. So the local planner comes up with the trajectory. Like if this is already into your, let's say XY coordinates of the points that you want to follow. Maybe you have some optimality constraint on the trajectory. Maybe you want to avoid some obstacle. But basically the goal of the local planner is to take the car from the current position to a go point and then generate the trajectory in between. And then lastly, we have the control module. So this is basically that the module that, given a trajectory, how do you track it? And then how do you correct for errors that in your, say in your throttle or in your steering? And today we're going to talk about one of those tracking algorithms, which is called pure pursuit. So before we start, we're going to make a few assumptions. The first one is the vehicle is given a sequence of 2D positions, or as we call it, waypoints in the map that you want to follow. The second one is that the vehicle knows where the given waypoints are in their own frame of reference. So the underlying assumption is that given a set of waypoints in a global coordinate, you can localize your vehicle and then transform them into your local coordinate. So this is where the cartographer and particle filter from last week come in. And then lastly, our goal is just to follow these waypoints. All right, any questions? All right. So we're going to start from a very simple geometric interpretation on how to actually come up with the steering angle. So basically, if you think about it, there's very easy ways to track a waypoint, but not very accurately, right? For example, if you have a waypoint in front of you on the right, you can set, you can check if a waypoint is on the right or on the left, and then you can set an arbitrary positive or negative steering angle to basically try to go that direction, but you only have a general idea on where the waypoint is. You don't really know how to set the steering angle correctly. So if we want a slightly more accurate representation of what the car is doing, tracking the waypoint, we can start from the vehicle's local frame. So as we mentioned before, the local frame's origin is at the rear center of the rear axle on the car. The x-axis is the forward direction of the car, and y is the left. To the left of that is right-hand coordinate. So it's always going to be like this on your car. And then we're going to introduce a concept of look-ahead distance. So this is basically you're looking ahead at a fixed distance and you're searching for a waypoint in your list of waypoints to track. This is going to be a parameter of the algorithm. Anybody have questions on that one? Yeah.
So is, I was wondering, is this a standard usually for a coordinate system? Because I know like in aerospace, northeast down is the standard. I'm just wondering why it's not northeast down here.
I think this is standard for vehicles,
Okay.
like ground vehicles.
I was just wondering if that's what you would see when ground vehicles are they still be northeast down even though they don't have it.
It's not northeast down, it's going to be up for this.
Okay.
Any other questions? So this is basically you're setting a look-at distance, and you're trying to look for a waypoint, basically in that radius. Is that point clear? All right. So let's say we figure out some way to find the goal point, and we're going to denote it by x and y. And since our robot is not hologramic, so you can't just turn to that direction and go straight to that waypoint, right? So we have to follow an arc because we have acronym steering. Is that point clear? Because you can't just directly go to that point, you have to follow some arc. Right? So we draw an arc. Question, so do you see a problem here? Yeah, what's the problem?
It might run into an obstacle.
We're not considering obstacles yet.
Oh,
Yeah,
Maybe goal point so that the turning radius is too tight.
that's one question, but it's more like,
The heading at the end of the curve?
huh?
The heading at the end of the curve?
No. Yeah, this is not dynamically feasible, not a dynamically feasible solution, so it's not an MPC. You're not going to get any of those guarantees from this. But the problem I was trying to state is the arc might not be unique, right? You have, yeah, you have 2 points. You might have multiple arcs going through them, or like infinitely many. So how do we make it unique? Any ideas? How do you define least distance? Yeah.
yeah, that's what I was saying, sir.
Maybe you pick like the shortest arc that doesn't have a turning radius that's like too sharp for your car or something like that.
Is it easy to find an arc in terms of the arc length? Like you have infinitely many solutions possible. Yeah. How does that change the arc? Remember, there's no dynamics in here yet.
Oh, yeah.
It's actually very simple to constrain this. Yeah.
Or shouldn't it just be like the arc length is longer, the
Arc length is longer.
like the further it is from just going a straight line.
So you mean like so you should go straight as much as possible? Is that what you mean?
I guess the
It's easier than that. Like I think there's more. We're just constraining, having one constraint so that there's only one arc. Kinda. You're getting closer. Yeah. So what we do, we just constrain the center of the arc to be on the y-axis of the vehicle. So like the arc here is going to be tangent to your axis. So that will constrain the arc that you'll have. Right? So we put the center here, we'll have a radius for the arc. And then basically this is a y coordinate, or the absolute value of y of your goal point. And then this is the absolute value of x of your goal point. Is this clear? Any questions? Yeah.
I don't understand how we choose D.
D is not something that you're choosing yet.
Yes.
So you know that the constraint is only that the center is on the y-axis. So this is not a known value yet. So you only know x and y right now.
Okay. So we just constrain one thing, but D is...
Yeah, you're going to basically solve for this.
Oh.
Won't your goal point change as you keep moving?
Yes, we're going to talk about how to update this. So this is only in one frame right now. So like if you need to come up with a steering angle at one frame, this is basically what's happening. Okay. All right, so now, since you asked, we're going to start solving for some of these values. So two very obvious things, since this is constrained so that this would be a radius of the arc. So r is equal to absolute value of y plus this d value. And then we also have d squared plus x squared is equal to the radius squared. And then next, we'll substitute out the d as r minus absolute value of y. And then expanded, we have this, and then we can, since we have the look-at distance here is L, we can have x squared plus y squared equals L squared. We substitute that in, and we'll end up with the last one. And the next step, we can get rid of the radius square. And then basically we'll come up with a relationship between your look-at distance, the y coordinate of your go point, and the radius of the arc. Any questions? All right. So how does this help us? Since we know the radius, we could figure out what the curvature of the arc is. Right? So basically, the curvature is going to be 1 over your radius. So that's going to be 2 times absolute value of y divided by your look at distance squared. And like you can see that steering angle should be bigger when you have a higher curvature arc, right? So this is going to be a proportional. The steering angle is proportional to the curvature of the arc. So basically, what you can do to come up with a steering angle is you solve for this arc gamma, which is the curvature of the arc that you're chasing, and then you can do a P control. Yeah, basically a P control on this so that it's proportional to the curvature of the arc. Right. So as we mentioned before, the look at distance that you choose, it's a parameter. So that L is something that you control. Yeah.
I have a question. So, since the steering is on the front, shouldn't the axis also, the origin also be on the front? In that case, then we can just find the tangent of that curve at that point, and the rest of the body of the car will just follow.
Yes and no. It doesn't, like, this is not very exact. We're just saying that the steering angle is proportional to the curvature. That's all we're saying, and we're not explicitly giving out any gains on what this relationship should be. Yeah.
Is it also accurate in steering, so it should be off of the radius when it turns is based on the back axle rotation?
Yeah. But this is implementation details that you could experiment.
Well, it just makes sense to have the back rotate around that.
Yeah. All right. So your question before, how do we update the goal point? So as I said before, that only happens every frame. So that's only for one goal point. So now that you know how to find a relationship between the goal point that you want to follow to actually coming up with a steering angle, how do we pick a current waypoint? Right? Say you have a list of waypoints. This is just random waypoints. And your car is over here. And the next thing you set is basically the look at distance L, right? So in an ideal world, what you would do is just pick the waypoint that's exactly one look at distance away, right? But so you just find the one that's exactly the closest one to you that's exactly one look at distance away. Does anybody see a problem? A very obvious one is that it's not going to always be there, right? So what if there's no waypoints exactly one look at distance away? Any ideas? Yeah.
Well, I just say a problem could be if you choose the closest one, it might not always be where you want to go, I feel like.
Oh, yeah, that's one of the problems. So if you imagine you're going to have two, right? If it's just a circle away, you're going to have one in front, one in the back. So this way, you'll have to constrain your search somehow so that it's actually going the direction that you want the car to go. Yeah. So any solutions for this problem? Yeah.
Just the intersection between the circle and the line between the next two waypoints, or the closest one that's in the circle, or the furthest one that's within now, and the next closest one that's outside of that.
Yeah, that's one idea. So basically, you're choosing. It's actually the second scenario. So you're basically choosing, as you said, right? The furthest one from the car inside the circle, the closest one outside the circle. You're basically drawing a line and then interpolate at exactly one look at distance away. So in this case, what should the look-at distance be when you're calculating the calculating the curvature of your arc? So what should L be in that equation we saw before? Right, it should be exactly, it should still be L, right? Because you're interpolating at L. Is that point clear? Yeah, and another solution is that you can pick the next fast one, right? Either the one that's closest to you outside the circle, or the one that's inside the circle but further away from you. It's going to be less accurate. So in this case, what should the L be when you're calculating the curvature of the arc? Yeah, it might
It should be a little bigger.
right. It should be the actual distance from your car to the waypoint that you selected instead of the L. Is that point clear? We went the other directions, it might be less clear. Okay. Also, if you can think of some other solution, you could also use that. This is just like two very easy examples. So one way to do the updating scheme of your current waypoint is basically every time, so you're going to see this when you start running the particle filter. Basically, the particle filter is going to listen to your laser scan message, and then it's going to update the guess for the current post. So your pure pursuit is going to be basically subscribing to the particle filter's topic. And then each time you have a new post, you could find the current waypoint based on the look-at distance that you chose, and whatever scheme that you chose to pick the waypoint. Either pick the closest one to the look-at distance, or interpolating the two and find the exact one that's one look-at distance away. And then you can calculate the steering angle based on that waypoint that you have selected, and then publish a steering angle based on that. And then once you get a new post, you do this over and over again. So basically, every time you get a new post, you're going to search for a goal waypoint, calculate the steering angle, and then move towards that. Is this clear? Any questions?
I'm getting a little ahead, but is our binary just going to be generating a bunch of waypoints?
So we're going to talk about how to come up with waypoints later, but this is not coming up with the waypoints.
Yeah.
This is basically if you have already have a set of waypoints, how do you want to track it?
Yeah, I just think of how dense or sparse the waypoints
So you're going to have you're going to start experimenting on that when you actually implement this on the car. Yeah, you'll see the effect yourself. All right, so based on that, we just described. So basically, every time you get a new pose, you find waypoint, you change your steering angle, and keep doing that. You'll have some curve that's not exactly following the waypoints. As you imagine, there's going to be errors. Right? And updating the goal point. You might have some other way to update the current waypoint. You can come up with your own solution, but the one that I just showed is the simplest one. All right, so tuning the pure pursuit. There is only one parameter, as we discussed before, the look-at distance. So basically, a smaller look-ahead will lead to more aggressive maneuvers. So as you can imagine, since the that equation before. Right, since your L is going to be smaller when you have a short look-at distance, which means that your curvature is going to be higher, which means your steering angle will be higher for like a given waypoint, right? So you'll see a lot more aggressive curve following. Right, you're going to see the swerving. So the swerving is caused by basically steering delay in the servo. As you can imagine, if you give it a steering command, it doesn't immediately goes to that angle, right? Your car is going to travel further up and then slowly turn to that radius. By that point, you're going to overshoot, so you're trying to correct yourself again by setting it to the other side, so you're gonna have this oscillation around the waypoints. Yeah.
Is that kind of like follow the gap has it oscillates so bad? Is it delayed, or is it just because that's a little more inherently algorithm?
Follow the gap, I think it's more because of the sudden change in the gap. But this is like, this is more like a PID control where you just have too high of a peak.
Okay.
Right? As we saw before, it's basically proportional control. It's proportional on the curvature. Right? If you have a smaller L, you're going to have a high curvature for the arc that you're tracing, and then your P gain goes up, and around the equilibrium, you're going to have a lot of oscillations. So a larger L, you're going to have like a smoother trajectory, but it's going to have higher tracking error, basically. Right. Any questions? All right. So tuning the L, I'm going to put another thing there. Tuning the L and tuning basically the gain on your transforming your curvature into your steering angle. You could put a gain there, but I usually just use it as is. You could put a gain there. So tuning those will change the behavior of pure pursuit. So, for example, in the Levine loop, for example, you have 90-degree turns, right? You want to be very careful not to have too big of a look-ahead distance. If you imagine if you're going around the corner, your look-ahead is already here, when you're not even at the turn, you're going to start turning and you're going to hit the inner corner. So right, just be very careful about that. Right? So the waypoints that we discussed are only a sequence of 2D points. So you could also put in a velocity component at each position of the, basically every single waypoint, you can also give it a velocity that you want, right? You could come up with a velocity profile with some smarter way, or you could just basically hand tune it, right? As some of the teams did in reactive methods, right? If you have a higher steering angle, you're going to lower the speed. You could kind of do the same thing here, where you just put like lower velocity around the corner, higher velocity on the straights, right? You could do something like that. Right, as we said before, pure pursuit doesn't consider the dynamics of the car as just simple arc, and then you're assuming that your car is going to be able to follow that arc, but it might produce dynamically infeasible curves or arcs. Right, so that keep that in mind. If you have too small of a look ahead, it might just go crazy and then crash into the wall. All right, so now putting it all together, how do we use the cartographer package? How do we use particle filter lines? We kind of went over this, but basically the first step is, Matt, I think we already assigned this. So you're going to have to create a map with cartographer. So basically you're going to do that on second floor of the beam around the loop. So you're, as you see the map in the simulator, it's all straight walls, right? But it's not like that in reality. There's doors that curved in. There's some different, the door at the elevator is different now, so it doesn't look exactly like the map. So the first thing you do is you create a map using cartographer. And then you need to create a list of waypoints using a global planner. Right now you don't have anything. So the easiest way is to drive around the track with teleop, and then you can record the poses that particle filter gives you as the list of waypoints. So we already have a node that allows you to do that. And then afterwards, as you imagine, if you're recording it with your driving, your car's going to be faster at some time, slower sometime. You might have stopped there. There's going to be multiple points at the same, basically same location on the map. So what you'll want to do, if you choose to do so, is to basically create a spline with all the points that goes around the track. So there's a lot of packages that could do this. Basically, SciPy, interpolate, splurt. That's one option. So what you will want after you record the waypoint is find a way to smooth out the path basically, and maybe have equispaced waypoints on the track, right? And then you're going to spin up your particle filter node. You're going to spin up your teleop node. You're going to localize in the map, and then once you're able to localize, you can subscribe to the post topic, and then do the updating scheme that we've discussed. Right? You're going to pick a new current waypoint every time you get a new post. Send out a steering angle, update a pose, and repeat. All right, so short video. So it's you're gonna be able to run the car a lot faster, and then you're gonna have basically more control over what path the car is gonna take. This is another one. This is from last October. The competition that we ran in Colombia. So this is one of the peer pursuit solutions. As you can see, it slows down around the curve. As soon as it hits the straight, it starts accelerating. So in your implementation, you could also have control over what velocity you're going to set at each waypoint. Right, and you can see like it's able to correct itself even if the tail starts spinning out.
Did you have to hit those outlet bumps or whatever they are?
Thanks for good lighters.
All right. Any questions before I go into the lab for today? All right.
I just wanted to clarify how to get those waypoints. Like, are they fixed once you get it from Teleop and they never change?
You can change them. Huh?
You can repeat the question.
So the question is, how do you come up with the waypoints? Can you change the waypoints once you've recorded it? So usually the waypoints are going to be, if you're using only pure pursuit implementation, the waypoints are usually fixed before you run the pure pursuit. But after you record it, you can have your own smoothing algorithm to basically come up with a better line around the track. Yeah, and later on we're going to introduce some, say like a trajectory generator using MPC. Then you'll have a changing list of waypoints, basically.
Like, my question is, suppose you know the path you want to take around the track, you have some trajectory.
Yeah.
Why can't you just sample from that to get a waypoints?
Wait, say that again.
Why can't you just sample from like a trajectory to get a waypoints?
Like randomly sample the trajectory?
Yeah, something like that.
So you have to have some constraint on that, right? So you can't just say like, if I want to sample one of the waypoints on the other side of the track, that's not going to work.
I mean, I just feel like we know the localization of the car,
Yeah,
and we know what our path should be like.
yeah.
So I'm just wondering why we can't take points from that trajectory instead of having to record it beforehand.
Right, you still have to come up with the first trajectory in some way, right? The recording is just one way to generate that. You could also, like, say, have an image and click points and then generate the waypoints.
Yeah.
Right? You don't have to record it. It's just one way to do it. And then for your sampling question, we're going to go over some of the motion planning stuff next lecture. So we're going to talk about RRT, which is sampling based local. Any other questions? All right. So today's lab. I hope you all got started on installing cartographer and particle filter on your car, because those take quite a bit of time. And then once you install that, you should try to make a loop, try to make the map of the loop upstairs. So let us know if there's any issue with that, because in the previous years there's a lot of issue with the odometry where it won't be a 90-degree turn. Sometimes the map it just goes really bad during the loop closure. Yeah, after you're done coming up with the map, you can test your particle filter. see if it actually localizes with the laser scan. Let us know if there's any issues installing them. And then lastly, you can start writing your code for peer pursuit. So another thing is that, I think Matt mentioned it, in the particle filter you want to set an initial close for the car so that the particle filter doesn't have to wait or like run multiple iterations before it settles on one point. So you can give it an initial pose where it will have a really high confidence starting with. So in order to do that, you'll need to have a remote desktop. So I think everybody's still using SSH before this. So with this, you can actually see Argus and then control the car with the remote desktop. So we use X11 VNC. Basically, these are the steps to get it started and running. I'm going to post the slides on Canvas and Piazza right afterwards, so you can get started with that. Yeah, and then once you install and started the X11 VNC server, you can use a client on your desktop, laptop, phone, iPad, whatever. So Remina is the one that comes with Ubuntu. If your laptop has Ubuntu, you should already have a VNC client. So there's another one called VNC Viewer. I think it's free. You just have to register, I think. And then to connect, you type in your car's IP, and the default port is 5900.
So you just replicate the same network.
Yeah, the same way that you did the SSH before. Yeah. So race 2. So basically race 2 is going to be, you're going to be using the map-based approach that we just described. So you're going to have a map, you're going to localize, and then you're going to use peer pursuit to go around the track. So we're still doing one car time attack. So it's the same format as last race. And our scoring criteria is we're gonna adjust it because you guys are gonna be way faster this time. So it's